Hi everyone, this is Brett Sanders, and this is the fourth instructional video for PRIMo. And by now, some of you have surely noticed that all of the simulations we've looked at thus far have involved the options Landcover setting being set to 1, which means that the file, the PRIMo, is loading a Landcover data set and it's using that information in some way. Yet as of thus far, I haven't explained what PRIMo is doing and what the input looks like. So let's backpedal a little bit and go back to the PRIMo prep script. When we ran the PRIMo prep script, it loaded a TIFF file containing a digital elevation model, and it also loaded a TIFF file containing a Landcover classification where pixels were assigned a number of 1, 2, 3, 4, 5, an integer number that corresponded to different Landcover classes. So when we ran that PRIMo prep script and it loaded that information, one of the first graphics that comes up here is this one, which shows both the digital elevation data and the Landcover data. And what was going on in the PRIMo prep script was that we were trimming this raster to be a nice whole number of even in rows. So we trimmed the edges of this to go from some arbitrary number of rows and columns to a whole number, which lends itself nicely for upscaling. So we trimmed the model a little bit, the rows and columns, so it came out to be 1,400 rows and 1,600 columns. And these two data sets are on the same resolution, same spatial extent. And this one here, you can see, has numbers that go from 0 to 10. So there's 10 different Landcover classes. So when PRIMo reads that in, given that this option is set to 1, then it will use another file, which I'll have to create a new Finder window. So inside this PRIMo-GPU Miami Gate, there is another file called the Landcover file. There it is. So I'll open that file up. And there you can see that this is yet another table. And the table formatting starts with the title, in this case the number of classes in the Landcover classification. There's 10. And then the table headers, which are an ID, the impervious fraction associated with that Landcover, a Manning N for that Landcover, and then a name, which is optional. The model won't read in this name, but it's handy to have it there just as a reference of how you've laid out your Landcover classification. So here we start off with channels and roads being completely impervious, so those are set to 1. The Manning coefficient, for whatever reason, is set to 2 different numbers. There is a beach classification, which is assumed to be completely pervious with a different Manning coefficient, and so on and on you go. Now, impervious fraction will be interpreted to be a runoff coefficient when the seepage functionality is not activated. So scrolling down to the input, you'll notice that there's an option to model seepage. And when this option to model seepage is turned off, then this number will be taken as a runoff coefficient. And so say if 1 centimeter of rainfall falls, then the amount of rainfall that becomes runoff will be the runoff coefficient times that 1 centimeter. And the other fraction will be categorized as infiltration, but it won't be routed anywhere. It'll just be infiltrated into the ground, and it'll be effectively a sink into the simulation. This file has some additional information here and here. These are just older versions of tables that I've cut and pasted and placed down here just as a reference in case I wanted to kind of throw in some different distributions for a different simulation. So as of now, that is the distribution of runoff coefficients that are being used by the model for these 10 different land cover classes. And when we run the model and then visualize the output in PRIMo-Viz, for a base case of just precipitation on the model grid, you can see the water accumulates. And now if you wanted to then change the imperviousness so it's you get more runoff, we could in principle say I might want to save this as an example, save this as for reference later. I cut and paste it back in. Let's just assume everything is 100% impervious, and we should get a bit more runoff than we did the first simulation. So it's just like an example of how you can edit the file. The water hardly flows, it hardly moves, so there's not a whole lot of sense in studying sensitivities to the Manning n here. But so sensitivities to the impervious fraction, now it's set to 1. This will maximize the amount of runoff. And why don't we go ahead and run that. I can't even guarantee that when this model completes, you'll see something different in the animation, but may not be that perceptible because a lot of this site is buildings, and there's so many buildings, and they're already treated as being impervious. So, but we'll see. Okay, the model's done. This was sort of the result that we saw before. Ponding of water. Now everything is impervious. We can run that model again. And are we seeing deeper, more water on the land surface? Maybe we could imagine that's just looking just a little bit wetter than the previous simulation. But that's the gist behind the land cover classification and how you can configure it to represent different types of land surfaces and their impact on runoff.